We can refer to solutions qualitatively as dilute, having a small concentration of solute, or concentrated, with a large concentration of solute. We also express concentration quantitatively a few different ways. The first is mass percentage. The mass percentage of a component is the mass of the component in the solution divided by the total mass of the solution times 100%. Just like any other percentage, it's the part of a whole. For very dilute solutions, for example, if we were looking at the amount of a solute present in seawater, we could use parts per million multiplying by 10 to the sixth, or parts per billion by multiplying by 10 to the ninth. Since concentration expressions are often based on the number of moles, we'll also use mole fraction. Remember that mole fraction is the number of moles of one component divided by the total number of moles of all of the components. And we'll also use molarity, which is moles of a solute divided by liters of the solution. Remember, that's the total solution, solute and solvent. But since volume is dependent somewhat on temperatures, chemists also like to use molality to express concentration. And molality is moles of solute per kilogram, that's mass, of solvent, not the total solution, but just the solvent. This mass is not temperature dependent, the way volume can be. Solutions behave differently than pure solvents. Pure water freezes at 0 degrees Celsius, but adding salt to water will cause it to freeze several degrees lower. That's why they salt the roads before it snows, so the roads hopefully don't freeze up. Adding salt to water also raises the boiling point of the water. Physical properties that depend on the quantity of solute particles are colligative properties. The word colligative means depends on the collection. And these are the properties that we'll focus on: freezing point depression, vapor pressure lowering, and boiling point elevation. Remember that vapor pressure is the pressure exerted by the vapor at equilibrium with its liquid. And then substances that have vapor pressure are called volatile. If we add a non-volatile solute to a solvent, the vapor pressure is lowered. Because of the presence of this solute, more of the liquid is prevented from moving into the gas phase. This relationship is expressed by Holt's law, which states that the partial pressure exerted by a solvent vapor above a solution, or P sub A, equals the product of the mole fraction of the solute in solution, or X sub A, times the vapor pressure of the pure solvent, so vapor pressure, or the partial pressure of the solution, is equal to the mole fraction of the solvent in this case, multiplied by the vapor pressure of the pure solvent before anything's put into it. So then, the greater amount of solute that's in the solution, the smaller the mole fraction will be, the less able those molecules are able to form a gas, lowering the vapor pressure. The next of the colligative properties that we'll take a look at is boiling point elevation. My mom always used to tell me that you should put salt in the water when you cook pasta because it cooks faster. We'll see if that's true. Remember that boiling point is the temperature at which vapor pressure is equal to atmospheric pressure. If, by adding solute, say salt to water, our solution will have a lower vapor pressure than the pure water did. So it'll take more energy for liquid water to change phases to a gas. The solution is going to boil at a higher temperature. We can calculate a change in boiling point by multiplying the boiling point constant by the molality of the solution. Let's go back to our pasta problem. We're going to take a liter of water and we're going to add a mole of sodium chloride salt to it, and we're going to figure out what the new boiling point is going to be. Remember, 1 mole of sodium chloride is equal to 58.44 grams. That's about a quarter of a cup of salt. Let's start by determining the molality of the solution. Our solvent is water, and we have 1 liter of water, which is 1,000 milliliters. And since the density of water is 1 gram per milliliter, if we have a liter is 1,000 milliliters, which is 1,000 grams. When we put sodium chloride in water, it dissociates into sodium ions and chloride ions. So that 1 mole of sodium chloride actually then is forming 2 moles of ions. So what we will do then is multiply our number of moles by 2. And so the actual molality in terms of particles then is going to be 2 molal. Plugging that into our equation, the boiling point elevation constant for water is 0.52 degrees Celsius per molal. Plugging that into the equation, we're going to calculate a change in temperature in the boiling point of... The boiling point of water is 100 degrees Celsius. We just calculated the change in the boiling point. And since it's boiling point elevation, we're going to increase the temperature, the boiling point, by 1.04 degrees Celsius, giving us a new boiling point of 101.4 degrees Celsius. And remember, we added a whole mole of sodium chloride, about a quarter of a cup. Nobody would ever put that much in their pasta. So, sorry, Nana, but I don't really think that the pasta was cooking any faster. But it does raise the temperature a little bit. So putting sodium chloride into water will raise the boiling point, but putting sodium chloride into water will also lower the freezing point. And we can also calculate the change in the freezing point by multiplying the freezing point constant by molality. And again, remember to take into consideration the number of particles or ions that are formed in the solution. So what would be the freezing point of a solution that contained 26.22 grams of sodium chloride in 800 grams of water? Well, again, let's start with our molality. Remember, molality is moles of solute per kilogram of solvent. Converting grams to moles, we get 0.4487 moles. We'll multiply that by 2 to account for the number of particles that form. And we'll divide that by our solvent. 800 grams of solvent is going to give us 0.8000 kilograms. That gives us 1.12 molal. Multiplying by our freezing point depression constant, we get a change in boiling point of 2.08 degrees Celsius. And since the normal boiling point of water is 0 degrees Celsius, our freezing point is lowered by 2.08 degrees Celsius, giving us a new boiling point of negative 2.08 degrees Celsius. The number of particles in a solution also affects many biological systems. Osmosis is a process that allows the movement of one less concentrated solvent through a semi-permeable membrane to another more concentrated solvent. One example is red blood cells. This is a normal red blood cell. It's at equilibrium with the fluid surrounding it. But if it were surrounded by a solution with a higher concentration of solute, or these solutions will try to reach an equilibrium. And so since the solution outside of the cell has a higher concentration of solute in it, water then will move from the cell, out of the cell, and into the solution to try to dilute it to the same concentration that's inside the cell, leaving us with a red blood cell that looks like this guy. Or we could put our normal blood cell in a solution that is hypotonic, with a lower concentration of solute. Again, these solutions through osmosis will try to reach an equilibrium. And since the concentration inside the red blood cell now is greater than that which is on the outside, then the water from outside the cell will move into the cell to try to form an equilibrium. And we end up with a red blood cell that looks like that. So if our cell is in an isotonic medium, the concentrations of the solution outside of the red blood cell are equivalent to that which is on the inside of the red blood cell. If we put our red blood cell in a hypertonic solution, one that has a high concentration of solute, then water will move out of the red blood cell and into that high concentration to try to lower it to bring it to the same concentration that was inside the blood cell. So the cell shrinks. If we put our cell into a hypotonic solution, which has with a lower concentration of solute, then the water is going to move into the red blood cell to try to form an equilibrium, causing the blood cell to swell and eventually burst. Another example of osmosis, don't try this at home, is putting salt on a snail or a slug. These guys now have a really high concentration of salt outside of their little bodies. And so what's happening is that the fluids inside their little bodies are moving out of their bodies to try to reach an equilibrium. And so the little guys will just shrivel up and die. And it's a really painful way of dying, I would imagine. So again, don't try this at home. Snails are people too. So we've talked about solutions being homogeneous mixtures. They appear to be uniform throughout because the solute and the solvent are indistinguishable from one another, as opposed to homogeneous mixtures, where it's very easy to see the different phases that are present. But in between these two, we have colloids. Colloids are particles that are larger than molecules, but not so large that they would separate out of the solution, dispersed in another substance. They can be solids, liquids, or gases in any combination with each other. Whipped cream is an example of a colloid that is a gas in a liquid. Marshmallows are a gas dispersed in a solid. Milk is a liquid in a liquid or an emulsion. You can tell that a substance is a colloid if it exhibits the Tyndall effect. If you shine a light through the substance, you can see the beam of light in the colloid as it's scattered by those larger particles. You won't see the beam of light in a true solution. The Tyndall effect is also evident in this beautiful sunset. The light from the sun gets scattered through dust or pollutants in the atmosphere. In the human body, we have enzymes that function as catalysts for the many chemical reactions that keep us functioning. Enzymes are one type of colloid. They can be hydrophilic or attracted to water. Look, hydrogen bonds. Here too. These polar groups on the surface of the molecule are attracted to water. Or they can be hydrophobic, like sodium stearate, which the majority of the molecule is nonpolar hydrocarbon with a slightly polar and also hydrophilic end on it. Hydrophobic molecules generally fold up so that their hydrophilic ends are not at the surface. And that keeps them from dissolving in water.